It's Friday. We've got one more assignment due for the week, and then we can enjoy our weekend. So let's get to it. Today we're talking about fossils. I think a fun topic for a Friday. So, what are fossils? What are we talking about? So, when we say fossils, this is the remain or evidence of any ancient or super old living thing. So, if you had something that was alive like millions of years ago and it died, and then it was buried and went through a lot of pressure and heat and a lot of specific processes that we don't got to know too much about, it can create a fossil. So a fossil can be bones of a big scary thing like this, or it can be like, here's a dragonfly. Dragonflies do not have bones, but its little teeny tiny body was saved as a fossil. But it doesn't have to be just an animal. It can be a plant. So like here's a super old leaf that made an indent in a rock. So that is also a fossil. Now, scientists who specifically study fossils, they have a giant, massive collection of fossils that they use to study, and we call that the fossil record, the record of fossils. That's pretty easy. So the fossil record, scientists can look at it to study more about maybe what did the earth look like millions of years ago. Because if we have evidence of what lived there, we know, well, obviously we know what lived there, but we know what the environment may have looked like. We know what might have been going down on the earth at that period of time. Now, we can also use the fossil record to compare different fossils of the same species through different time periods, because that can help us see how that species may have evolved, right? So we remember that when something evolves, that it changes. So we can see, like, if we know that this is one species and we study it for 50 MYA, just means millions of years ago. So here's that species 50 million years ago. Here it is 35 million years ago. Here it is just 3 million years ago. So we can see how its bone structure has kind of shifted or changed or evolved over the course of millions of years. Just as a reminder, also if you're looking at two structures from two different species, so let's say you're looking at the fossils of a lizard compared to another type of lizard, I don't know, the more similar two different species look when you're looking at their bone structure or their fossils, the more likely they are to be related or share a common ancestor. We know this, we've been talking about that nonstop. You can think about yourself. You look a lot more like your siblings or your cousins than you do to me, because we're not related. I don't think so. So since we're not related, we look more different than you do to someone you're related to. So the same thing works with different species. Okay, now this, I think we got this stuff down pat, but just as a reminder, we can figure out the relative age, how old different rocks and fossils probably are based on their location within the earth. So the youngest fossils are always going to be toward the top or closer to the surface of the earth, while the oldest rocks or fossils are always going to be at the bottom. And it makes sense because this was a long time ago. A long time ago, that animal or plant was living on top of the earth. So pretend that this, I'm trying to cover it with my hand as if you can see that happening, as if these layers weren't there yet. And then that animal died and was buried. And then suddenly we had a new top of the earth. So that living thing was there and then died and was buried. So the closer to the surface of the earth, the more recent that living thing existed and was up living its life, and then it died and was buried. So the youngest is always going to be at the top. So in this case, fossil A is the youngest, and the farther down you go, they get older. So B is older than A, and C is older than both of them, and D is super old. It's older than all of these fossils combined. The fancy term we use to call this whole ordeal, the term for this is the law of superposition. Just in case you see in a test question where they say, based on the law of superposition, they're just asking which is the oldest, which is the youngest, all that nonsense. So that is the law of superposition. Now, when we talk about index fossils, I know this might make some of us cringe a little bit because it is a little difficult, but I think it's one of those things that when you practice it, it gets a lot easier. But to be honest, I will be shocked if they ask you a question about index fossils when you're taking the MAAP test. They're really going to be asking you about over here, this law of superposition. But just in case, you never know. It's been a crazy year, so who knows what they'll throw at you. If we know the exact age of a certain fossil, so like let's take a look at this fossil right here. If we know this fossil is 15 million years old, we can use it to figure out the age of that same fossil in a completely different spot in the earth. So like here, let's say in column Y, we're digging up fossils in Como. Sure. And column Z is a piece of the earth that we dug up in Sardis. So we're in two different spots in the earth. So if we know the age of fossil 3 over here in layer 3, if it meets certain standards, we can use that to figure out the age of a fossil in a different location. So if that fossil is present in a short period of time, so meaning it's within just one layer of a specific place in the earth, so like here fossil 3, we don't see it in this layer and that layer and that layer and that layer. No, it's only in one layer. It's only in one spot. And it is also all the way over in a different part of the earth, but also in a single layer. So like if you look over here, and this is our Sardis layer, we have the fossil, again, it's the same fossil, but it's just in one layer. So since it meets those standards, we know that, okay, if this fossil over here in Como is 15 million years old, then we know that this fossil must also be 15 million years old. And that is just what we call the index fossil. If it meets those standards, if we are able to use it to guess the age of another fossil, that's an index fossil. So if this fossil were in like layer 4 and 5 and over here in layer 7, 8, that would not be a good index fossil. We need it in just one period of time. Okay, moving on. We also talked a long time ago about how that fossil record can help us create a timeline of the earth. So I talked about how, we can study everything that is inside the fossil record to learn more about Earth's past. So that is what we're talking about here. We can use the fossil record to create a timeline that we call the geologic time scale, which we've talked before. When you see the prefix geo, that just means Earth. So we're creating a timeline of the Earth's past. Pretty cool. So we use fossils to actually divide up different periods of time. So I think the easiest thing to think about is, I'm sure most of us have heard of Jurassic Park, right? That's when all the dinosaurs come to life. So it's called Jurassic because all of the dinosaurs were really alive during the Jurassic time period. So when we see dinosaur bones, we know we're talking about the period of time that was the Jurassic time period, which if you look at this scale, it goes down in millions of years. And remember, the top being closest to recent, the farther down, the older or more long ago it was. So the Jurassic time period is like 145.5 million years ago. So we know that long ago is when there were dinosaurs. So we use all kinds of different things, different fossils, not just dinosaurs, to figure out different periods of time. So if we see certain fossils that are no longer alive today, just like the dinosaurs are, we know, okay, that certain fossil is related to the, let's just pick one, Permian time period. So we know, okay, it was around 252 million years ago. So we really use all of the fossils to create this beautiful timeline of Earth's past and give these different periods of time different names. Now you might see, I don't expect you to know the difference between these periods of times, but these are all just like measures of times. I think we've heard of era, like if somebody says this is the end of an era. Era is just like a certain period of time. So if you ever see, especially like over here, you see different labels of time periods like eon, era, period. That's what I keep saying. They're just talking about a certain amount of time. You do not need to know how long an eon is or how long an era is. Just know that if they are pulling that up, that is what they're talking about. It's just a period of time. So in this case, since we're talking about the history of the earth, all of these are measurements of the number of years, still can't spell, years before present. So how many years or eons before today? That's kind of what it's asking. Again, you don't need to know the ins and outs of all of this. I just don't want you to look at a test and say, eons, eras, what is that? Just know it's a period of time, okay? Don't let it freak you out. Last slide. Last thing that we really hit up about fossils, and I think this is kind of an interesting one. The other thing that fossils can tell us is when we have a big extinction. So we remember, most of us knew this coming into the 8th grade already. Whenever you see an entire species, let's think of the dinosaurs because that's easy. Whenever you see an entire species completely die, like they no longer exist on the earth, that is what we call that extinction. So we can see when extinctions in the past have happened because we have a large amount of fossils. So think about the dinosaurs. We have a large amount of dinosaur bones, and they never carried on past a certain time period. So like let's say 150 million years ago, within that time period, we saw a bunch of fossils, but we never, for dinosaurs, but we never see any more dinosaur bones after that or that are younger than that. So we know that they didn't exist past that time period. They were extinct. So anytime a large number of fossils is present at a certain time, we know that they must have gone extinct, meaning they completely died off. Now we have these things called mass extinctions. So a mass extinction is when all at once something happens causing multiple species to die out. So not just dinosaurs, maybe a certain type of bird and then a bunch of types of plants. They all completely died all at once. Kind of scary. So that is what we call a mass extinction. Now we've had, I believe it's 5 total mass extinctions in the history of Earth. You don't need to know them by memory. You don't need to know like when they happened and what they killed. You just need to know that there are certain events that cause those mass extinctions, I cannot talk, those mass extinctions to actually happen. So any crazy event, and they have to be crazy to kill out all of these things at once. These are things that we call catastrophe. And I'm sure we've heard the word catastrophe before, but usually people use it when they're just being dramatic and something goes wrong. We say, this is a catastrophe. Well, these events that cause the mass extinctions really are catastrophes. They are horrific, sudden, unpredictable events. These can be asteroids raining down on the earth. That's what killed the dinosaurs. So they killed out a lot of different species. If you have a massive, and I'm talking massive flood, that can cause a lot of extinctions, or a giant, and I mean a giant volcanic eruption that covers like half of the earth. Obviously, that's not too great. So that also will kill out a bunch of species. So these are examples of catastrophes or catastrophic events that are going to cause a lot of species of animals or plants to go extinct. Here is your cheat sheet. Not much on this cheat sheet either, but just a reminder that the youngest fossils are at the top, the oldest fossils and rocks are at the bottom. A reminder of what it means for a species to go extinct and what can cause an actual mass extinction. Here is just an example of the timeline or time periods that you see different extinctions. So like here is the Triassic or Jurassic. So we see a lot of dinosaurs that were alive and then went extinct and never returned, and just a bunch of different examples. This is how they will probably picture it. Last thing I want to talk about here, this is something that we got down pretty easily when we first learned all this stuff, but I don't want us to forget it. That if we are looking at a characteristic of a fossil, which we're about to do in independent practice, we can make a lot of assumptions, meaning we can guess what is true about that animal just based on its body or its bone structures. So for example, if we see the fossil of an animal that no longer exists, that fossil is extinct, and it clearly has wings, It's safe to say that if an animal has wings, it was probably able to fly, right? Duh. Or if you see a fossil that clearly had fins or gills, like a fish would, we know, okay, that living thing must have lived underwater. So there are a lot of things that when we're just looking at the fossil, we can say, yep, it probably did this or probably did that, which is exactly what scientists do when they're looking at those fossils. That's how they learn so much about old living things from the past. I also made a separate cheat sheet for index fossils just to really break it down further. If you're like, lady, I don't even know what you're talking about with index fossils, please help me out. Here is just another cheat sheet that really gives it some good examples and really breaks it down. Okay, for our independent practice, we have, it's nothing too crazy, it's pretty simple. We have 2 slides that I want us to take a look at. Let me move myself way out of the way. So what you want to do here, we've got a picture, and I know it's a little blurry, I'm sorry, I did my best. We've got a little picture of different fossils within different layers of the earth just hanging out, doing their thing. So what I need you to do is using the fossil names listed in this column, I need you to order these 4 fossils in order from oldest being number 1, to the youngest being number 4. And you can do that based on where they are located in the fossil layers, right? So, for example, let's just do the first one. The oldest, we know the oldest fossils are always going to be at the bottom, right? So if we look at the bottom here, layer A, we've got, that word is trilobites. Trilobites is at the bottom, and that's one of the words we need to put in order. So the oldest, I'm going to type trilobites. And then just keep going up. What is slightly younger than that one? And then what is slightly younger than that one? And then what is the youngest? Pretty easy. A lot of these fossil names, by the way, are kind of wild, like Neptunia. What kind of name is that? Don't let it trip you out. You don't even need to be able to know how to pronounce it. You don't need to know what it means. Just know that is a name, and just look for that name, look for the word that matches it, and you're going to be set. Don't let these crazy words freak you out or anything. You don't need to know them. You don't even need to know how to pronounce them or read them correctly. They're just letters in a random order. This last piece before your exit ticket, because you got to do your exit ticket, this diagram right here shows a reconstructed image of the, and there's another crazy fossil name, I don't even know how to pronounce that, so I'm not even going to try, of one of the oldest known fossil animals with features labeled. Okay, so here is an example of what that animal would have looked like. We know it had large eyes, teeth in its jaw, he had wings with claws, scary, long feathered tail, all that good stuff. So based on these features that are labeled, what are 2 things that you think would have been true about either this animal's behavior, so what are things that it would have done, or about its environment, so where would it have lived? So for an example, I already gave you an example. Since it has wings, it must be able to fly. Duh. So take a look at other things like it has teeth. What can we assume it must have done since it has teeth? What can we assume it could have done since it has large eyes? And just give me 2 different examples from specific things in this diagram that you can assume is true about that fossil. Don't you dare copy my example. That's lazy. I won't give you credit for it. I just won't. So once you're done with that, just do your exit ticket. It's pretty short and sweet. And then you're done for the day. You're done for the weekend. I'll see you on Monday.